All right, so get ready, because today we're diving deep into something pretty mind-bending. We've got this physics paper, and it's proposing something that's pretty radical.
Yeah, it's
Whole new way to look at the
a
universe.
new way to understand the universe, yeah.
Basically, the fabric of reality.
Mm-hmm.
And we're looking at this paper. We're calling it New Paradigm.
Okay.
And it suggests that maybe we need to rethink some of our most basic assumptions about how reality works.
Yeah, it's not just like tweaking some of the existing theories we have. This is like a complete paradigm shift.
Yeah.
It suggests we need to start from scratch and think about a single dynamic entity they're calling changing space or Cspace.
Cspace.
Instead of these familiar concepts like spacetime.
So instead of picturing the universe as this like stage where all these particles are interacting, it's like saying that the stage itself is the main player and it's constantly changing and shaping everything on it. Yeah.
So it's kind of like those old sci-fi movies where reality is like this giant pulsating blob, right?
Well, I mean, the analogy might need some work, but you're getting at the core idea.
Yeah.
This shift in how we think about the universe has some pretty wild implications.
Okay.
Like, the possibility of a variable speed of light.
Whoa, okay, hold on.
Yeah.
Variable speed of light.
Imagine a universe where light traveled at different speeds.
I mean, how would that even work?
It's mind-blowing to think about. Would galaxies have formed differently?
Right.
Would time be totally different?
I mean, the speed of light is like a fundamental constant, right?
Right, exactly.
It's built into all the equations that describe how the universe works.
It's what we base everything on.
Yeah, what would it even mean for that to change?
That's where New Paradigm gets really interesting.
Okay.
It draws this distinction between what it calls structural properties and behavioral properties.
Right.
Think of it like a rubber band.
Okay, a rubber band.
It's elasticity, that's a structural property.
Right.
How much it stretches,
yeah,
that's a behavioral property.
Okay.
It depends on how much force you apply.
So are they saying that the speed of light isn't really a fundamental property of the universe itself?
Mm-hmm.
It's more like something that emerges from how this Cspace behaves.
Exactly. And it's not just the speed of light.
Oh.
They argue that other constants, like Planck's constant and the gravitational constant, those are also emergent properties.
Okay.
They arise from the underlying structure of Cspace.
So they're not like defining it.
Right.
They come from it.
Exactly. They're not fundamental to the structure itself.
So let's talk about this Cspace.
Okay.
How do they even describe it? It sounds pretty mind-bending.
They describe it as a three-dimensional space that can deform over time.
So like imagine
it's kind of like a cosmic jello mold constantly jiggling and reshaping itself.
And then there's this rigid time dimension that acts as a universal clock.
Oh, okay.
So the key difference here from our usual space-time picture is that the resistance to deformation, or like the stiffness of this Cspace, can vary from place to place.
So the stiffness changes.
Yeah, it's not uniform throughout.
Okay, and that's what could lead to a variable speed of light.
That's the idea.
Okay, I'm trying to wrap my head around this.
It's a lot to take in.
So imagine Cspace was incredibly stiff in the early universe, like way denser than it is now.
Right.
Light, or any disturbance really,
Yeah.
would move through it very differently than it does today.
Exactly. And this variable stiffness could maybe explain why gravity seems so weak compared to the other forces.
Right, gravity is like the weakest force.
What if the Cspace is just super stiff right now in our current epoch, making gravity's effects really subtle?
So the constants that we observe, they might just be like a reflection of our little local patch of Cspace.
That's the suggestion.
It's like trying to understand the ocean by studying just a single wave.
Exactly. We're only getting a limited perspective.
Yeah, we're missing the bigger picture.
Right. A new paradigm suggests that all these familiar concepts, space-time, particles, even quantum phenomena, they all emerge from this underlying Cspace picture.
So it's a totally different way of looking at things.
A complete shift in perspective.
All right, so we've got this wild idea of Cspace. But how does it actually explain the stuff we see in the universe?
Right.
Like, how do things like gravity and quantum entanglement fit into this picture?
Good questions.
We need some serious unpacking here.
Definitely. Let's dive into how this new paradigm tries to bridge the gap between the fundamental Cspace and the physics we know and love.
I'm ready.
Let's do it.
Okay, so we've said that Cspace is this like dynamic, always changing thing.
Right.
But how do we get from this cosmic jello mold to the particles that make up you and me and everything around us?
Well, New paradigm suggests that what we see as individual particles are actually localized deformations in C-space.
Localized deformations.
Think of it like knots in a piece of fabric.
Okay, knots.
The way the fabric is tied creates different kinds of knots,
right,
each with their own properties.
So instead of picturing these tiny billiard balls bouncing around, we should think of them more like knots or ripples in the fabric of C-space.
That's a good way to visualize it.
Okay.
And just like the properties of a knot depend on how the fabric's tied.
Right.
The properties of a particle, its mass, charge, and so on, arise from the specific way that C-space is deformed in that region.
Okay, that makes sense.
Yeah.
But what about forces?
Okay.
How does this framework handle something like gravity?
Right.
I mean, we usually think of gravity as this force of attraction between objects with mass.
Yeah, in this picture, gravity's not really a force in the traditional sense.
Oh, okay.
Instead, it emerges from the way these localized deformations in C-space influence each other.
Right.
Imagine two knots in a piece of fabric.
Yeah.
They're not actually attracting each other.
Right.
But just their presence distorts the fabric around them, creating kind of a flow that draws them closer.
So they're not really pulling on each other? It's the way they're warping the fabric of space-time around them.
Precisely.
Okay.
And this model could even explain why gravity seems so weak.
Yeah.
Compared to the other fundamental forces.
Right, right.
If C-space is like super stiff right now, as we were talking about earlier, it would take a massive amount of energy to create significant deformations.
Okay.
Meaning gravity's effects would be relatively subtle.
But what about the quantum world?
Okay.
How does this framework deal with things like quantum entanglement?
Right.
Where particles seem to be connected in ways that defy our classical understanding of space and time?
That's where things get really interesting.
Okay.
Remember, in this framework, everything comes down to this single interconnected entity, C-space.
Right, right.
So if two particles are entangled, it's not that they're sending secret signals back and forth faster than light.
So entanglement is still real. It's just we've been misinterpreting it because we're stuck in this framework of separate particles.
Exactly. By shifting to thinking about the underlying C-space, those seemingly bizarre connections between particles make more sense.
Okay.
They're not two separate things communicating across vast distances.
Right.
They're two different aspects of the same underlying deformation in C-space.
So it's all connected.
It's all one thing.
Okay.
Think of it like two sides of the same coin.
Okay. Two sides of the same coin.
They're inextricably linked, even if they appear separate.
This is really making me rethink everything I thought I knew about physics.
It's a big shift.
But let's step back for a second.
Sure.
And address the elephant in the room. How do we even know if any of this is actually true?
Right.
Does this model make any testable predictions?
That's a key question.
Yeah.
And New Paradigm acknowledges that much more exploration is needed to develop concrete, testable predictions.
Right, because a cool philosophical idea is one thing.
Yeah.
But if we can actually test experimentally, that's a whole other level of validation.
Absolutely. It has to be grounded in reality.
So what about those tests?
It does suggest some potential avenues for experimental verification.
Okay, I'm all ears.
Particularly in the realm of cosmology.
Cosmology, okay.
Remember our earlier discussion about the variable speed of light?
Yeah.
If light did travel at different speeds in the early universe,
right,
that could have left traces in the cosmic microwave background radiation.
The afterglow of the Big Bang.
Exactly.
Yeah.
By studying the patterns and polarization of this radiation, we might be able to find evidence that supports or refutes this idea of a variable speed of light.
So we could look back in time, billions of years, and see if light was behaving differently than it does today.
Potentially, yes.
That's incredible.
It would be a huge discovery.
Yeah.
And that's just one possibility.
Oh.
Another avenue lies in gravity.
Gravity, okay.
If gravity is really a consequence of how C-space deforms, there might be subtle deviations from Einstein's theory of general relativity.
Okay.
Particularly in extreme gravitational environments.
So like black holes.
Black holes, neutron stars, places like that.
So by studying those cosmic heavyweights, where gravity is super strong,
exactly,
we might be able to find clues about whether this C-space model holds up.
That's the hope.
Okay.
Of course, these are just a few possibilities. But the point is, even if this specific model isn't completely accurate, it opens up entirely new lines of inquiry.
Totally.
That could lead to unexpected discoveries.
This is what I love about these deep dives.
Me too.
We get to explore these radical ideas
This new perspective could actually help bridge the gap between science and philosophy.
Okay, how so?
Well, think about it. By viewing the universe as a single, interconnected entity, we start to blur the lines between the observer and the observed.
So instead of seeing ourselves as these separate beings studying an external universe, we're more like expressions of the universe itself trying to understand its own nature.
Exactly.
We need to move beyond just the concepts, develop the math in more detail.
The mathematical underpinnings of Cspace need to be fleshed out.
New paradigm is still pretty theoretical right now.
It's a starting point.
We need the math to really see if it holds up.
That's how we'll know if it's viable.
Another challenge is connecting the Cspace picture to all the experimental data we already have.
Right. We can't just throw at everything we know about physics.
We have to see how this new paradigm incorporates it.
And explains those observations. This is just one proposal.
Right.
One possible path toward a deeper understanding of the universe.
So, as always, more research is needed.
Always.
But even if this Cspace model doesn't turn out to be the ultimate answer, it's definitely sparked a fascinating conversation.
What's that people thinking?
It's challenged us to rethink some of our most basic assumptions about reality.
It's expanded our horizons.
Well, listeners, I don't know about you, but my mind is swirling with new ideas after this deep dive.
It's been quite a journey.